Alright, so what's going on? In this video, we're going to look at maximum and minimum values. Alright, so we're getting ready to start graphing. Okay, so first thing we got to do, let's look at this. Graphing will be, I don't think the next lesson, but it will be the one after that. Alright, so let's look at these definitions here. So let C be a number in the domain D of a function f, then f of C is the absolute maximum value of f on D if f of C is greater than or equal to f of x for all x in D, and it's an absolute minimum value of f on D if f of C is less than or equal to f of x for all x in D. All right, so in other words, we're finding that point in the domain, okay? Because see, D represents the domain. So we're finding that C value that's in the domain of the function that is either the largest value possible, which is your absolute maximum, or the smallest, which is your absolute minimum. All right, and then we have another definition. The number f of C is a local maximum. Now, notice the difference. The first definition we looked at was absolute maximum and absolute minimum. Now we're looking at local maximum, local minimum, and I'm going to show you the difference in them. Okay, so local maximum value of f if f of C is greater than or equal to f of x. Okay, so look, it's saying the same thing so far, right? But local maximum when x is near C, and a local minimum value of f if f of C is less than or equal to f of x when x is near C. All right, so notice the absolute max and min, that's for all x in the domain. It's either the largest or smallest. But for local maximum minimum, it's when x is near C. Okay, so let's look at the difference. So here's something so you can picture it. So we have a graph here. So this graph, notice how it comes down, it goes back up, and then comes down again and goes back up. Now, this graph, it just keeps going to infinity. As x is going to negative infinity, y is going to infinity, and as x goes to positive infinity, this is going to positive infinity also. But you can see that this value right here, that's the smallest value that this graph has over its entire domain. Okay, now I'm not saying it's going to be over when you're looking for absolute max and min. It's not, or absolute max and min, it's not going to always be over the entire domain of the function. And you'll see later on when we work some of these problems that they say, okay, what's the absolute maximum and minimum value of this function on this interval? Okay, so they may tell you, we just want to know on this interval. But right now we're looking at the entire domain, but you can see there's no value that's smaller than that. So that's an absolute minimum. But it's also a local minimum because it's the lowest value near this point. Okay, see, near whatever x value we have, it's the smallest value that's near this x value. All right, now this value right here is just a local maximum. Okay, this right here, that's just a local maximum because you can see there's values out here that are larger than this. So we can't say it's an absolute maximum, can we? All right. And then right here, this point right here, we have a local minimum. It's a minimum. It's not the smallest value on the graph, but remember what local minimum says is when x is near C. That's local. That just means right around this area. It's the smallest value. Now, this graph here, it doesn't have an absolute maximum, does it? I mean, how could it? Because I mean, what's the largest value on this graph? Well, the y value. What's the largest y value? Well, it's going to infinity. We're not going to have one. Okay. So hopefully this graph helps you understand the difference between absolute and local max and min. Okay, that's all we're doing right now. Okay, that's all we're doing. We're not necessarily trying to find these things right now. It's just we want to be able to look at a graph and kind of tell, is this a local max min? Is it an absolute max min? Is it both? Okay, that's what we're looking at, just to be able to identify. And these examples here, these are some good examples of looking at local max and mins. So all we're doing here is we're just graphing this. Okay, so I've got 0, and hopefully we still remember how to graph sine and cosine, especially the basic ones, right? There's 1, there's -1. Remember, if we graph it here, let's see. So I just want to look at this graph, and and this graph just keeps going forever, right? Keeps going on and on forever. All right, so f of x, let's just talk about the local max and mins here, and the absolute max and mins. Well, where are the absolute max and min values for this one? Okay, where are they? Well, there's a bunch of them, isn't it? You see that? There's a bunch of them. This has an infinite number of local max and mins. See, 1, 1, -1 here. And remember, this thing just repeats itself over and over and over. So it has an infinite number of local max and min, because see, it's the largest value in this area, in this area, in this area, and of course that's going to continue on to infinity and to negative infinity. You got an infinite number. And then we also have an infinite number of absolute max and mins. Can you see that all of these points here? See this graph, what happens with cosine? We know cosine is never going to get larger than 1. It's never going to get smaller than -1. So each of these points are also absolute max and min values. Okay? So hopefully that helps you see that. All right? Now, let's look at this one. And like I said, all this is just it's to help you see the difference between local and absolute. Okay? Now what about this one? Of course, this is our point. That's a minimum, right? So can you guess, or do you know, not guess, but do you know what is that? Well, it's a local max and min, right? Because it's the smallest point in this area. But it's also an absolute min, right? Because there's no other point that's smaller than that. Okay? And right now we're looking over the entire domain of the function. Okay? Because it didn't give us any restrictions, did it? It just said f of x equal x squared. And I know I don't have any other directions there, but what they're wanting us to do is identify. They're wanting us to look at local max min, absolute max min. Well, this problem here has both. This right here is both absolute min and a local min. But once again, there's no absolute max, no absolute max, no local max. All right, because this graph just keeps going to infinity. All right. All right, now what about this one? Here, if we look at this, that's the graph, right? That's the graph of x cubed. All right, so what would this one have? Well, can you see this one has none. It has no absolute max or min, and it has no local max or min. Because, I mean, if you look at this just keeps decreasing, right? It's decreasing, and this keeps increasing. There's nothing in here. Okay, let me do that in a different color. But there's nothing in here where we can say, well, that's the largest or smallest point, value. So, it has nothing like this, or, like we did up here. There's nothing where it increasing, then it decreases, or decreases, and then see how this decreases, and then it starts increasing. We have nothing like that here. So this has nothing. It has no local or absolute max or min. All right, now what about this one? This is f of x equals 3x to the fourth minus 16x cubed plus 18x squared. But look at this. They only want us to look at this graph from -1 to 4. So they're restricting the domain that they want us to look at it on. All right, so let's graph this thing. All right, so we got what? -1 and let's see, 1, 2, 3, 4. All right, so we've got this point here, and then we've got 0, 0, and then we've got this point, and then this one, and then we have this one. So this graph looks something like that. Now, this is the point -1, 37. This is the point, obviously you can see that's 0, 0. This is the point 1, 5. This is the point 3, -27. And then we don't have a point for that. I mean, we could get it. We could plug 4 into the function and get it, but it's really not that important right now anyway. So the one thing that you might be wondering is, how in the world did you know to graph that thing like that? Well, I looked at a picture of the graph and copied it. Okay? These are the types of functions that you're going to learn how to graph in not the next video, but the next one. Okay? When you learn to graph these things like this, this one's an easy one. Okay? It's easy to know, to see how to graph this. Just be patient. Wait till you get to that section in your calculus class. Right now, it's not important. It's not that important in this section that you know how to graph that. All right. And I mean, and you could use some, You could use some algebra to do it if you wanted to, but calculus would make this one easier. All right, so all they're wanting us to do, look at this graph and let's identify the points. Okay, so let's look. You see here we have a local minimum. You see that? This would be a local minimum. What about this one? This would be what? A local max. What about this one? This 3, -27. That would be a local and absolute. Not max. Min. Right? Now, let's look at this. This point -137. This would be what? An absolute max. Okay, look at it. If we look at the height of it, in this interval from 1 to 4, it's the largest value. Okay? So it's an absolute maximum. Remember what absolute maximum says. An absolute maximum value of f on D, and what's D? It's the domain of f of c is greater than, okay, so the absolute maximum value of f on D if f of c is greater than or equal to f of x for all x in D. And look at this. We passed it up. This is D right now. They're restricting it from -1 to 4. Okay? From -1 to 4. So this is the largest value on that interval. So it's an absolute max. But it's not a local max. It's just an absolute. All right? Because to say it's a local, well, that has to, it's the largest value in that area. And we can see, and I mean, this is going to keep going. But this is it's just a absolute max. Now what about this one? Well, that one's nothing. Okay? It's nothing. It's not a local max for min, and it's not an absolute max for min. Because it's not the smallest on this entire domain, and it's not the largest on the entire domain. So this one here is nothing. All right. So hopefully, from looking at some graphs and, things like that, hopefully now you can see that the difference between absolute and local. All right. All right, so let's look at this next thing, the extreme value theorem. So let's look at this. So if f is continuous on a closed interval AB, so closed interval, that means the A and the B is included, then f attains an absolute maximum value, f of c, and, notice that, and an absolute minimum value, f of d, at some number c and d in the closed interval AB. So what they're saying is, if we're looking over an interval and you have a continuous function, there is going to be an absolute max and there is going to be an absolute minimum. Okay, so this up here was a good example of that. Here's a graph on a closed interval. There is going to be an absolute max and there is going to be an absolute minimum between -1 and 4. And notice what it said, at some number c and d in, Now notice they included the AB when they said in the interval AB. They're including the AB. And this is a perfect example. See, there's your absolute maximum, and there's your absolute minimum. They're saying you are going to have one. You're going to have both if the function's continuous. All right, so here's some examples. So here we have a continuous function on AB. Here's our absolute max. Here's our absolute min. See, it's the smallest on the interval. This is the largest on the interval. This one, here's from A to B. Okay, so you can see we have an absolute maximum here at C. We have an absolute minimum at, well, they said at C and D. Well, in this case, D is equal to B. There's your absolute minimum. See, the endpoints can be included. All right. And then here, between A and B, well, there's our absolute max. Well, we got two of them, don't we? So we could have more than one. So these are the same height. All right, so we got an absolute max at C1 and C2, and then we have our absolute minimum here at D. All right, so let's look at this one. Here we're on the interval from 1 to 2. So you can see here we have an absolute minimum at 2, right? You see that? We got an absolute minimum at 2. But this one, there is no absolute max. Okay? But, remember up here it did say, then F attains an absolute maximum value and an absolute minimum value at some number C and D. It's saying it has both. But so what's the problem? Can you see what the problem is? Look at this function. And what does it say? What does it say? That's the key thing there. That's the important part. If F is continuous on AB. And you can see here, this function is not continuous, so we're not going to have, we're not going to have both. Could we have both? Yeah, I'm sure there's a situation where you could have both. Okay, but this one you don't, because I know you may be thinking, well, look at that point. Isn't that a absolute maximum? No, because this number here, this value here does not include 3. So what's your absolute maximum? What would it be? Is it 2.9? Is it 2.99? Is it 2.9999? You see where I'm going with it? We can add 0.9s forever. Okay, so there's no absolute maximum there. And then this one, what about this one? There is no absolute max and no absolute minimum. There's none in this. Okay, see, this right here, this graph is just increasing forever. And here, well, what's the lowest number? The 1 is not included, so is it 1.0001? How many zeros, and then you want to add and then tack a 1 on? Okay, so there's none in this one. So there's an example where there's no absolute max, no absolute min. And what's the key thing here? Well, you can see here that, see the 0, see 0 and this 2. This interval, this graph does not fall on this interval. That's no. It falls on this interval, 0 to 2, because notice the x value does not include 0, and this graph does not hit 2. So, that's on an open interval, and plus it's not, well, it's on the open interval 0 to 2. So it's not going to follow this extreme valued theorem. All right. All right, so let's look at Fermat's theorem. Okay, so hopefully, I know this may seem kind of boring here, but it's important that you understand this. Okay, remember, it's not about can I work the problem. It's about do I know why I'm doing what I'm doing. Okay. All right, so let's look at Fermat's theorem. So if f has a local maximum or minimum at C, and if f prime of C exists, then f prime of C is equal to 0. Oh, well, that's pretty neat, isn't it? That's telling us if f has a local maximum or minimum at C. Okay, so if there's a local maximum or minimum, that means I can take the derivative of the function, right? I can take the derivative of the function, and whatever makes that derivative 0, right? See that? Whatever number makes the derivative 0, okay, or that local max or min value, right? The x value, if I take that x value of the local max and min and I plug it into the derivative, then I'm going to get 0 as an answer. So that's pretty interesting there. And it says, and if f prime of C exists. Okay. So what some students might think, oh, well, look at that. I can find a local max and min now. Now remember, we're talking about local max and min. So I can find a local max or min. All I've got to do is take the derivative, set it equal to 0, and solve for x. Right? And then, because isn't that what this is? Whenever the first derivative is 0, so I can just set it equal to 0 and solve for x. Ah. Well, can we think of it like that? Well, let's see. Let's look at this. We've got f of x is equal to x cubed. Now, in this problem, well, we know that the derivative is 2x squared, and 2x squared is equal to 0 when x is equal to 0, right? So that would mean, okay, if we thought about it, like I just, like I said, oh, well, we can take the first derivative, set it equal to 0, and that'll give us our local max and min. So that means we would have a local max or min at x equals 0, right? Well, let's look at this. Isn't that the graph? That's the graph, isn't it? There's no local max or min there, is it? No, so that didn't work out, did it? And then let's look at this one. We've got f of x is equal to the absolute value of x. Well, if we look at that, well, there's the graph of absolute value, right? That's the graph of our absolute value function. So, what about this one? Well, this point right here, that point right there is actually an absolute and local minimum value, right? So what about this one? What I want to get over to you on this one is this absolute max min value. It can't be found by taking f prime of x and setting it equal to 0. Okay. Why is that? Okay. Well, f prime for this function, f prime of 0, okay, does not exist. Okay. The derivative at 0 does not exist. So at this x value here, the derivative does not exist, but it is an absolute and local minimum value. But the derivative does not exist. Keep that in mind. Okay. Now, I'm not going to go through and show how this does not exist. I do this in a previous video. It is, the title of the video would be, I'll tell you, I'll put a link in the description where I worked that. I show that it's the video I did where we're doing the definition using, we're finding the derivative using the limit. Okay, it's that video. Let me look. I'm gonna pause the video and I'll come back and I'll tell you which video it is. Okay, so it's called the derivative as a function. It's that video. It's in this playlist. But if you look up calculus, the derivative as a function, in that video, I show that the derivative of absolute value of x does not equal 0. All right. But what's the point of these two examples? Well, the point of these two examples is you have got to be careful when you're looking at Fermat's theorem. You've got to think. Okay, you've got to think. It says, what does it say? If f has a local maximum or minimum. Okay, so if we do have a local max or min, and the derivative of c, the derivative of the function evaluated at that x value exists, then f prime of c is equal to 0. Okay? Do not read this thing like it says if f prime of c equals 0 and f prime of c exists, then there is a local max or min. That's not true. What is that called? That would be what? The converse of Fermat's theorem. Okay, if you read it the other way, if this, if this part, then all of the other stuff. Okay? But just because we're taking the derivative, setting it equal to 0, that doesn't mean there's a local max or min there. That's not what it's saying. What they're saying is if it is a local max or min, then all that applies. Okay? All that applies. But it's not saying if this applies here, if we do this, then we're going to have a local max or min. So don't read it like that. All right? And that's where you got to be careful. Because, we just showed right here. Yeah, this one has an absolute and local minimum. But what was the thing? The derivative did not exist. Right? See, like it says here, the derivative did not exist. And this one, it just didn't have a local max and min. Just because the derivative is 0. Okay? Just because the derivative is 0 at x equals 0, that doesn't ensure that it's a local max or min. Okay, so be real careful about that. And look, we're going to do some more of these things, and let's look at the next video and the video after that. All this is real important. Getting ready to start graphing. All right, so we got a definition here. It says a critical number of a function f is a number c in the domain of f such that either f prime of c is equal to 0 or f prime of c does not exist. So what are we talking about here? We're talking about a critical number. A critical number of a function f is a number c in the domain of f such that either f prime of c equals 0 or f prime of c does not exist. All right, so let's take a look at this function, at these problems. It just says find the critical numbers. All right, so we're not finding local max or mins right now. Okay? We're not looking for that. We're not looking for absolute max or mins. All they're wanting us to do right now is find the critical numbers. This is so important to be able to do this. Okay, this what they're doing. They're getting you ready to start graphing. Okay, that's what this is. They're getting you ready to start graphing, and this is part of the process. All right. So if we find the derivative, so we got f prime of x is equal to 2x plus 3. And it says, well, look, this is what it says. Set the derivative equal to 0 and solve. That's what I'm going to do. So I get 2x plus 3 equals 0. So x is negative 3 halves. Well, first derivative is 0 there. There's my critical number. Okay, I mean, it's not undefined, right? Or, I mean, is this undefined anywhere? No, it's 2x plus 3. It's defined everywhere. So, because there is one where the derivative does not exist, okay? That can be a critical number also. All right, so what about this one? All right, so let's look at this. So let's take the derivative. So we've got f prime of x is equal to, so here we've got to do what? We've got to do product rule. So I've got 3/5 times x to the, what is that, negative 2/5, I believe that is. So times 4 minus x plus negative 1 times x to the 3/5. I believe that's right. Yeah, that's good. All right, so we got f prime of x is equal to, so, let's see, that's going to give us what? That's going to give us 3 times 4 minus x over 5x to the 2/5 minus x to the 3/5. I'm just trying to make sure I'm not making a stupid mistake somewhere. I'm making this video early in the morning, so if I get a common denominator, that's going to be, well, let's do this. This is going to be 12 minus 3x minus x over 5x to the 2/5. So that is going to be f prime of x is equal to 12 minus 4x over 5x to the 2/5. Okay, I got a common denominator. I'm gonna pause the video and I'm gonna make sure I didn't do nothing, a careless mistake somewhere. I'm gonna check my work again, because I'm sure I'll hear it in the comments if I don't. And I do see where I made my mistake. How about that? So it's a good thing I checked it. Common denominator is 5x to the 2/5, so this should be 5x to the 2/5. No, I'm sorry, just 5x. So that means this will be 8x, right? All right, so where are our critical numbers? Well, remember, in this case, f prime of x is equal to 0 when what? When 12 minus 8x equals 0. So that's going to be x is, what is that? 12 over 8, which is 3/2. So we have a critical number at 3/2 and at x equal what? 0. Why is that? because f prime of x is undefined at x equals 0. So our critical numbers would be 0, 3/2. That's our critical numbers. All right. So hopefully you're getting all this. So basically it's where what? It's where the first derivative is equal to 0 or undefined. All right. So let's take a look at this problem. We've got f of x equals 2x plus 1. So if we take the derivative, so we got f prime of x is equal to 2. We're using the quotient rule, right? Times x minus 2 minus 1 times 2x plus 1. And then that's over the denominator squared. Okay? So when we distribute, we get 2x minus 4 minus 2x minus 1 over x minus 2, x minus 2 squared. So we get f prime of x is equal to, that's just going to be what? Negative 5 over x minus 2 squared. All right, so in this case, f prime will never equal 0, will it? Because when is a fraction 0? When the numerator is 0. That numerator is negative 5. It's never going to be 0. Okay? But what did it say? It also said that we have critical numbers where f prime is 0 or where f prime does not exist. Okay? So we might think, okay, well, x equal 2 is a critical number. Okay? Because the derivative's undefined there. Well, that's not the case either. All right? So are you confused now? Because look, this derivative up here, it was undefined at 0, and that was a critical number, right? But why is 2 not a critical number? Because, I mean, the derivative is undefined there, right? So why is it not a critical number? Okay, be careful. Okay, watch what it says. A critical number of a function f is a number c in the domain of f. In the domain of the original function. Okay? Look. This function here, number 2, when we did it, the derivative was undefined at 0. Okay? It did not exist. Is 0 in the domain of this function? Yeah, we can plug 0 in. It doesn't break any math rules, does it? 0 is in the domain of that function. But look at this. The derivative is undefined at 2. Is 2 in the domain of this function? No. If I plug 2 in, that gives me 0 in the denominator. So that's the important thing that you've got to pay attention to there. We have a critical number. If C is in the, if C or that critical number, if that critical number is in the domain of the function, that's what you've got to make sure of. Okay? Where the first derivative is 0 or where the first derivative is undefined. That's where your critical numbers are, provided that those numbers are in the domain of the original function. All right? So you need to, if you're taking notes, you need to write that down and put a bunch of big stars by that, what I just said. All right, the closed interval method. So to find the absolute maximum and minimum values of a continuous function f on a closed interval a, okay? So now we're going to find maximum, absolute maximum and minimum value. So how do we do that? Well, we find the values of f at the critical numbers of f in the open interval AB. So that's not including the midpoints. Okay. And then it says find the values of f at the endpoints of the intervals. So what are they saying in there? They're saying in those first two steps. So basically what they're saying is, okay, find the critical numbers, okay, because it says critical numbers. So we want to take the critical numbers and we want to take the endpoints and we want to plug those values into the function and see what we get for our y values. That's what they're wanting us to do. All right. And then what does it say? The largest of the values from steps 1 and 2 is the absolute maximum value, and the smallest of these values is the absolute minimum value. So let's work a couple of these problems. All right. So find the absolute maximum and minimum values of the function. Now, for some reason, when I was writing these out, you know what I didn't do? I did not write the interval on this one. So this is from -1/2 to 4. Okay, there's my. So I'm looking for the absolute maximum minimum over this interval right here. All right, so what does it say? Evaluate the critical numbers and the endpoints. All right, so I've got the endpoints, -1/2 and 4. Now what I need to do is find the critical values. So to do that, I've got f prime of x is equal to 3x squared minus 6x. So I take this, set it equal to 0. That's 3x times x minus 2 equals 0. So x equals 0 or x equal 2. All right. So there's my critical numbers, 0 and 2. Okay, it's where the first derivative is 0 or undefined, and 0 and 2, they're both in the domain of the function. So I've got to, so step 1 says to evaluate the critical numbers. Step 2 says evaluate the endpoints. So basically what I'm doing is I'm finding the critical values and then I'm evaluating those and the endpoints in the function. So we've got f of 0 and we've got f of 2. So that's going to be what? 0 cubed minus 3 times 0 squared plus 1, which is 1. And this is going to be 2 cubed minus 3 times 2 squared plus 1. And that is equal to, let's see, f of 2 is equal to -3. And then I have f of -1/2. That's -1/2 cubed minus 3 times -1/2 squared plus 1. And that gives us 1/8. And then f of 4 is 4 cubed minus 3 times 4 squared plus 1. And that is equal to 17. So what do we have here? The absolute maximum. Okay. So absolute max is where? It's right here at 4, right? It's at the point 4 what? We need the y value. That's one good thing about these absolute max and mins. There's your y value right there. Isn't that how you get the y value? You take the x value, plug it into the original function. Well, that's what we did there already. So you have an absolute maximum at 417, and you have an absolute minimum. Well, which one has the smallest value? Well, that's right there at 2. At x equal 2, -3. So there's your absolute max, absolute min. Now, I know what some of you out there are probably thinking. Well, is Is the answer going to always, one of them going to be an endpoint and one of them going to be a critical number? Is that always going to be how your answer is? No. It just happened like that in this problem, but it's not going to always be like that. All right. But look, that's all you're doing right there. That's it. That's all you're doing. Finding the critical numbers and then evaluating those numbers and the endpoints into the original function. That's all you're doing. It's that easy. All right, so let's take a look at this last problem here. All right, so we've got f of x equals x minus 2 sine x. And I mean, this isn't the last problem. It's the last problem for these directions. And then we got a word problem coming up. All right, so let's take the derivative. So I've got, because I got to find my critical numbers, okay, working just like number 1. So f prime of x is equal to 1 minus 2 cosine x. All right. So let's set this equal to 0. So we get 1 minus 2 cosine x equals 0. So cosine x equals 1/2. And so x is what? Cosine of what is 1/2? 60. So that's pi over 3. If you don't remember how to solve these trig equations, you're already supposed to know how to do this. Okay, you're on into your first calculus class quite a ways. All right, so you're supposed to know how to do this. If you're having trouble with this, go search my channel for solving trigonometric equations. All right. Now, cosine is positive where? In the 4th quadrant. There's my reference angle. There's theta. And so I get what? 2 pi minus pi over 3. That is 6. So that's what? 5 pi over 3. All right. So now we have got to do what? We've got to evaluate the critical numbers and the endpoints into the original function. So I've got f of pi over 3. That's what? Pi over 3 minus 2 times sine of pi over 3. And then I've got f of 5 pi over 3, which is 5 pi over 3 minus 2 times sine of 5 pi over 3. And then I've got f of 0 is 0 minus 2 sine of 0. And then I've got f of 2 pi, which is 2 pi minus 2 sine 2 pi. All right, so let's see what we've got. So when we plug this into our calculator, we get negative 0.684853. We plug this one in, we get 6.9696839. Whoop. And then here, this gives me 0, and this is 6.28. All right. Now, if you're sitting there thinking, well, I punched all that in my calculator and that's not the answer I got. If it's not the answer you got, make sure your calculator is in radian mode. All right. All right. So let's see what we've got. Well, we've got an absolute minimum. Where? At pi over 3, right? This is the lowest value, 0.684853. And we have an absolute maximum where? Well, there's the largest one at 5 pi over 3. 6.968039. So there's your absolute max, absolute min. All right, so there's absolute max and min. All right, so let's look at this problem. And look, all this is just another, this is a absolute max min problem, just in the form of a word problem. Let's look at it. So it says the Hubble Space Telescope was deployed on April 24th, 1990 by the Space Shuttle Discovery. A model for the velocity of the shuttle during this mission from liftoff at t=0 until the solid rocket boosters were jettisoned at t=126 seconds is given by, and that's this velocity function, and it's in feet per second. Using this model, estimate the absolute maximum and minimum values. Okay, so we're looking for absolute maximum and minimum values of the acceleration of the shuttle between liftoff and jettisoning of the boosters. There we go. All right, so let's look. So let's write our function down. V of t equals 0.001302 t cubed minus 0.09029 t squared plus 23.61 t minus 3.083. All right, so we've got the velocity written down. So let's take the derivative, and the derivative of the velocity that actually gives us acceleration, doesn't it? See, acceleration. So that derivative is, now let's see, I don't know, let's say 0.003906 t squared. Make sure I got that right. So 0.00130 times 3, yep, minus, and then I'm going to multiply by, and then I take the derivative of this, 0.09029 times 2. I'm putting it in the calculator, make sure I get it right, because if I don't, I know I'll get the comments, oh, you don't know what you're doing. All right, 23.61. All right, so there's the derivative of the velocity. Now, let me ask you this. We set this equal to 0 and solve for t? No, we don't. All right, so you might think, well, we got to find the critical numbers because we're looking for the absolute max and min, right? And we're looking for it between what? Between t=0 and t=26. That's actually our 0 and not 26, but I think I said 26, but 126 seconds. That's the time interval we're looking for. Okay, because that's what it, say, from liftoff t=0 until the rocket boosters were jettisoned at 126 seconds. Okay, so now we don't set this equal to 0 and find the critical numbers. And why is that? Okay, read what the problem says. It says, using this model, estimate the absolute maximum and minimum values of the acceleration. So we want to know the maximum and minimum values of this function, of the acceleration. All right, you see what it's saying there? So I've got to take the derivative of the acceleration function. So a prime of t is equal to, so let's look at that. That is 0.007812 t minus 0.18058. All right, so that's nice. I mean, I'm kind of glad they asked us about to do the acceleration, because just think we would have had to, if we were doing the velocity, we would have had to put that in the quadratic formula, wouldn't we, to solve that? So it made it a little easier. So now we take 0.007812 t minus 0.18058. Set that equal to 0, so t is equal to 0.18058. And so that gives me t is equal to 23.12. All right. So now we've got to find a of 0, right? Remember, we're we're plugging this all back into this function, plugging the 0 in for t, and then okay, so just let you know, and this a of 23.12 and a of 126. Okay, how do you know I'm plugging it into a of t? Because it says it right there, a of 0. I'm replacing the t with a 0. I'm replacing the t with a 23.12. I'm replacing the t with the, not 128, but 126. Okay. All right. So I'm not going to write all those numbers plugged in for t. I'm just going to put down what they equal. So evaluated at 0, well, that one's easy. That's 23.61. And then at 23.12, that's 21.52. And at 126, that is 62.87. All right, there's that one. So the maximum acceleration, maximum acceleration is what? 62.87 feet per second squared. And the minimum acceleration is what? See, there's your maximum right there, right? And then your minimum, that's right there. And what is that minimum acceleration? That is 21.52 feet per second squared. And that's what the problem's asking you to find. All right. So I know this was kind of a lengthy video, wasn't it? But, you know, hopefully you enjoyed it. Hopefully you know something about local max and mins now, and absolute max and mins. All right. So thanks for watching, especially if you hung around this long. Check out my other videos. Give me a like, share, and subscribe. And I will see